Okay, problem 6 features Mr. Jarvis, who is running to catch a train at a constant speed of 5 meters per second, approaching from behind. When he's a distance d away, it starts to move with a constant acceleration of blah blah, 0.25 meters per second squared. Mr. Jarvis just barely catches the train. How much time passed and what's the distance? Excuse me, sorry about that. So, I just rubbed the pen against the mouth guard, or the microphone. Details you don't care about. Anyway, so we start with Mr. Jarvis being a distance d away. So there's some d there. Who knows what it is? We'll find out soon. And here is Mr. Jarvis. And here is the train initially. So this is, I'm going to say this is x for the train initially. And let's call that 0. And this is x for Mr. Jarvis initially. And I'm going to call that negative d. But to do that, I've already defined my coordinate system, haven't I? I've got to be saying this is the positive x direction, and this line right here is x equals 0. So this here is x equals negative d, which is where Jarvis starts initially. That's all fine. Okay, so let's see. Jarvis begins moving at constant speed, which is v, or is already moving at constant speed, which is constant velocity, which also means a constant speed, but more importantly, he's moving at constant velocity, plus 5.0 meters per second. Let me see if I can de-uglify that 5 a little. There we go. Meters per meter. Nice job. Meters per second. Okay, so he's moving at that, and then the train, velocity of the train initially is 0, but the train's acceleration is 0.25 meters per second squared. And so they travel out here, and then at some point, Jarvis catches the train. Okay, so at some point Jarvis catches the train. So at this point up here, when we get to this stage, x for the train final equals x for Jarvis final. And then the tricky part of this is Mr. Jarvis just barely catching the train. What does it mean for him to just barely catch the train? And that's kind of subtle, but that's the whole key of the problem, because right now we've got more unknowns than we have ways to find them. Okay, so what I want to show you here is what I mean by Jarvis just barely catching the train. So let's look at, let's look at an x versus t plot. So here's x going vertically, and here's t going horizontally. Okay, so the train starts off. I'll do the train in blue. Let's say the train starts off here. Okay, at x equals 0, with a initial velocity of 0, and then it starts to move as time goes up. So it accelerates like this, which means the slope of its x versus t curve is going to be constantly increasing, and it's going to look like a parabola. Okay, so this is a parabola here. Now, Jarvis starts off down here at negative x, right? And if he just barely catches the train, then what happens is he runs, and he just sort of barely you can see the train is going away. Right here, he just barely catches up to the train, and then the train starts to pull away. So if you just barely catch the train, what happens here at this spot is that not only are you at the same position of the train, you're also at the same velocity. And you can see this in your head if you think about you're running to catch the train, okay? And so you just barely catch up to it, and at that point when you've just barely caught up to it, you're like right behind it. You can reach out and grab the ladder and pull yourself on, and you're going the same speed, same velocity. But afterwards, the train speeds up and pulls away from you. And before that, you were closing in on the train, so the train was going slower. So in all this time here, the train is going slower, and then right at this point, you're matching speeds just at the instant you get to it, and then the train is going faster. This is what it means to just barely catch the train. Okay, so what this fills in for us is that the train's final velocity is equal to Jarvis's final velocity, which is constant, right? Because Jarvis was running at a constant velocity. So now this is all we need, because now it's pretty simple. So the train let's say we can say the train's acceleration, which was given, is going to equal the change in the train's velocity over the change in time. Okay, so I'm going to say we start at time 0, and then this here is the time when we actually catch the train, right there. So that's going to be t, right? So let's see, this Vj minus 0 over t. We were given a, right? So that equals a for the train. We were given a for the train. We were given Jarvis's velocity. So the time that passes, and that's what question A is about, how much time passed between the time when the train started to move and the time when Mr. Jarvis caught it. This time here. So that's not hard. We just solve for, yeah, and that becomes Jarvis's speed divided by the train's acceleration, because that's the time it takes the train to reach the same speed as Jarvis, right? So Jarvis was 5.0 meters per second. The train accelerated to 0.25 meters per second squared, and so that is going to equal 20, I suppose you can say 0.0 seconds, whatever. Okay, the time it takes is 20 seconds. Okay, and then what's the distance d? Well, that's a little trickier, but it's not very hard. What you need to do is find how far does the train go in 20 seconds, and then how far does Jarvis go in 20 seconds, and the difference is your d. So let me just move. Let's see. Where's my dang? Oh, there we go. There's my cursor. Jeez, it's hard to see. Okay. So what is the distance d? I'm sorry. This down here is an old problem, and that is me not realizing I was still in paint mode. Okay, there we go. So basically for part B, the distance d, okay, up there is how far Jarvis goes minus how far the train goes. Okay, so Jarvis goes, let's see, we have space. I'll move down to make space. Okay, so Jarvis goes, whoops, there we go. Okay, Jarvis goes at a constant speed for the time we found, t. Okay, that's how far he goes. And the train goes, well, the train starts at some initial speed of 0, which we're going to leave that turned off. So really it's 1/2 train's acceleration times t squared. Okay, so d equals Vj times t, and that is 5.0 times 20.0 minus 1/2 train's acceleration, which is 0.25 meters per second squared, and then the time 20.0 squared. So let's see, 20.0 squared is 400. Well, sorry, I'm going out of order here. Let's do this one first. 5.0 times 20.0 is 100.0, or 100 really. Whatever. Okay, minus 1/2 times, I don't need to write that crap in. Okay, so minus the 20.0 squared is 400. Divide it by 2 first to get down to 200, and then divide that by 4 is what's happening here. So minus 50.0. So d, final answer, equals 50.0 meters. And that is the problem of Jarvis and the train.